Multi-level feedback queue scheduling. Multi-level feedback queue scheduling is similar to multi-level queue, but a process can move between the queues. As you can recall, in multi-level queue scheduling, ready queue is partitioned into several different queues. Similarly, in multi-level feedback queue scheduling policy, ready queue is divided into different queues. The difference is in multi-level feedback queue, a process can move between the queues. This means a process can shift from one queue to the next queue. Whereas in multi-level queue scheduling, a process is not allowed to move between the queues. This policy uses dynamic priorities for the processes. Unlike the multi-level queue scheduling, where fixed priorities are used for the processes, this scheduling algorithm uses dynamic priorities. Dynamic priorities mean priorities can be changed from time to time. That is, the priority of a process can be changed based on its CPU burst time. So the criterion to change the priority of a process is CPU burst length. Based on CPU burst length, the priority of a process can be increased or decreased. For example, if a process uses too much CPU time, it will be moved to a lower priority queue. This means if CPU burst length is larger for a process, then its priority will be decreased. It will be moved to a queue that has lower priority. It allows IO-bound and interactive processes in the higher priority queue. Obviously, the processes that use too much CPU, these processes are CPU-bound processes. Hence, moving a CPU-bound process to a lower priority queue will leave IO-bound and interactive processes in the higher priority queue. In addition, a process that waits too long in a lower priority queue may be moved to a higher priority queue. This means if a process has been waiting too long in lower priority queue, then it can be moved to a higher priority queue. This form of aging prevents starvation. As you can recall, in multi-level queue scheduling, a process in lower priority queue may starve, because if there is a continuous stream of high priority processes, then this low priority process will not get the CPU. Hence, it may starve. Whereas in this scheduling policy, we are using dynamic priorities. So if a process has been waiting for a long period of time in a lower priority queue, then we can move this process to a higher priority queue. In this way, we can prevent this process from starvation. So how scheduling is done in multi-level feedback queue policy? A new process is always admitted to a highest priority queue where it is served in round robin. This means upon arrival, a new process will be allocated to the highest priority queue. And the processes in the highest priority queue will be scheduled using round robin policy. If a process doesn't finish in first queue, then it is moved to the tail of the next lower priority queue. This means if a process that has been in the highest priority queue and this process doesn't finish in its given time quantum, then this process will be moved to the end of the next lower priority queue. And in this lower priority queue, this process will be again scheduled using round robin policy, but with greater time quantum value. This means though this second queue is also using round robin policy, but the quantum value is increased. It is greater as compared to the quantum value that has been used in the highest priority queue. If the process doesn't complete in the second queue as well, then process is preempted to the next queue. This means if in the second queue, again process doesn't complete in the given time quantum, then this process will be moved to the next lower priority queue. It will be moved to the third queue, which is a lower priority queue as compared to the first as well as second queue. Processes in the lowest priority queue cannot be served until the queues above it have become all empty. This means a process in the, for example, a process in the third queue will not be given the control of CPU until the queues, that is the first queue as well as the second queue, the queues above it, they have all become empty. Let's take an example to explain the multi-level feedback queue scheduling. Suppose there are three queues in the system. The first queue has time quantum 8 millisecond. This means the first queue, which is the highest priority queue, this queue will use round robin scheduling policy and the value of the time quantum is 8 millisecond. The next lower priority queue is the, again, it will use round robin scheduling policy, but the time quantum will be 16 millisecond. And the lowest priority queue, which is the third queue, it will use first come, first serve scheduling policy. A new process will be admitted to the first queue. In this queue, the processes will be scheduled using round robin policy. And if a process completes its execution in the in its given quantum of 8 millisecond, then this process will exit the system. However, if a process doesn't finish its execution in the given time of 8 millisecond, then this process will be moved to the tail of the next lower priority queue. In this queue, this process will be given 16 milliseconds to finish its execution. Again, round robin policy will be used to schedule the processes in this queue. Now, again, there are two possibilities. Either the process will complete its execution or it will not complete its execution. If it doesn't complete its execution using 16 milliseconds, then the process will be moved to the next lower priority queue, where this process will be served using first come, first serve policy. However, a process in the lowest priority queue, it will not be served until the queues above this are all empty. This means the highest priority queue as well as the next lower priority queue, until these two queues have processes, then a process in the last queue will not be served. A process in the lowest priority queue will be only served if the queues above it, they both are empty. In general, a multi-level feedback queue scheduler is defined by the following parameters. The first question is the number of queues. How many queues will be used in a given system? Then it's the scheduling algorithm for each queue, that which scheduling policy will be used for every queue. And the third parameter is the method used to determine when to upgrade a process to a higher priority queue. That is, in case of starvation, if a process is starving in a lower priority queue, then which method will be used to determine that what is the suitable time, or in other words, after how long a process should be moved to a higher priority queue. The fourth issue is the method used to determine when to demote a process to a lower priority queue. That is, when a process will be moved to the next lower priority queue. And finally, the issue is the method used to determine which queue a process will enter when that process needs service. Either it is always the highest priority queue where a new process will be admitted, or it may be admitted to a different queue. As far as the strength and the limitation of this algorithm are concerned, its major strength is that this algorithm is the most general CPU scheduling algorithm. Based on its policy, the effectiveness of its policy, it is widely used as CPU scheduling algorithm. However, at the same time, it is one of the complex algorithm because the design of this algorithm needs it need answers to the questions that have been just represented. That is, we need to find the values for those five parameters that we have just explained. Until we don't have appropriate values for those parameters, it is which is difficult to arrive at a decision that what values will be used for those parameters. Hence, it increases the complexity of this algorithm.